Welcome back to this module on applications of probability. The next problem is another playful application of probability, the famous, some people may say infamous, Monty Hall problem. So, what is this problem about? Congratulations, you're the winner of a game show. You beat all the other candidates on this game show. It's the final moment for you to win a big prize, a brand new car, or go home with a goat. Here's how this Monty Hall problem works. You stand in front of 3 doors. Behind one of those doors is that brand new car that you can win. Behind the other 2 doors is a goat behind each door. You now get to pick one door. Let's say you pick door 1. Now, the game show host gets to open one of the other doors. He is not allowed to open the door that you picked, and he's not allowed to open the door with the big prize. He must open a door with the goat, or with a goat. And now the game is back to you. So he opens a door. Let's say he opens door 3, and behind door 3 is a goat. You pick door 1. Now, you get to decide. You can keep door 1 or you can switch to door 2. And then the prize is revealed. Either you're the lucky winner of a brand new car or the not quite so lucky winner of a goat. And before I tell you what to do, here's the in-class quiz question for you. What should you do? Should you keep door 1, the door you originally chose? Should you switch to the other remaining closed door, or it doesn't matter? So, what do you think? Did you think about this problem? Did you switch? Did you stay the same? Did you say it's 50-50? Doesn't matter? Now, you should switch. The answer is the probability of staying with the same door. You have a probability of 1 in 3 to win. The probability of switching to the other door is 2 in 3. So you can double your chances of winning by switching to the other door. Let's think about why that's the case. Let's go back to the beginning of the problem. There are 3 doors. You have no information. So all doors, I think we can agree, are equally likely. That's wonderful. We can use the definition number 1, the classical probability definition, or the objective definition that we've learned about at the very beginning of this course. 1 in 3. So the probability that you pick the right door, no matter which door it is 1 in 3. There's a probability 2 in 3 that you're picking the wrong door. I think we can all agree on this. 1 in 3, 1/3, 33 and a third %, you are right. 2/3, you have the wrong door. Let's think about this now. The 2/3 probability. That means there are 2 doors where there's a prize. But the prize can only be behind one door. So there's either the prize is behind door 2 and a goat in door 3, or the other way around. So the 2/3 probability includes the fact that behind one door there must be a goat, because there's only one car, not 2 cars. There must be a goat among those doors that you did not choose. Now the game host, the showmaster, shows you that door and that goat. You just didn't learn anything. Nothing changed. Your original probability was 1/3. The original probability was 2/3 that it's behind one of the other doors, and that included one goat. Nothing has changed. The game show host just made your life easy now, because that 2/3 is now essentially on that one remaining door. And therefore you should switch. Many people find this very counterintuitive. So let me try to give you another sort of explanation. Let's think about there isn't one door or 3 doors, but in fact there are 100 doors. 99 goats, 1 car. You pick again any door. Let's say again door 1. What's the probability that the car is behind that door? 1 in 100. Very unlikely that you pick the right door. Now the game show host opens 98 doors. Now think about it. 98 goats. Yeah, you knew there had to be 98 goats. Maybe 99 in the unlikely case you already had the car. Otherwise, he can choose. There are 98 doors that he has to open with those dumb goats. So, would you switch now? Yeah, of course you want to switch, because there was 1 in 100 before. It's going to be behind that other door, most likely. So I think some of the confusion stems from that it's only 3 doors. If you think about more doors, you will think, yeah, I definitely want to switch. I know this is very tricky, so let's now look at a Monte Carlo simulation of this problem in a spreadsheet. And I'm now going to simulate this game 1,000 times, and from the simulation create data, create proportions of winning by switching or winning by not switching, and then let's have a look at those numbers. So now, because we're looking at data, we're back to probability definition number 2. So let's go to the spreadsheet. Here's now a spreadsheet where I simulate this Monty Hall game show problem for you. Let's have a look at what I've done here. First, under price, there's a rand between 1 to 3. So this is a random number between 1 and 3, and that's the number of the door where the price is. So here in this example right now, it's a 2. The candidate chooses a 2. Again, a random number. I assume that the candidate is completely clueless and just randomly picks a number. Then the host has to open a door with a goat. Now here, this is quite a complicated Excel formula. You can ignore this. I know many of you can code this very elegantly and much faster than I did using Excel macros or Visual Basic. I deliberately did not do this here, so this will hopefully run on anyone's spreadsheet, on any type of computer, even older computers in the world. Then we look at what happens if the candidate does not switch, keeps the same door, or what happens if the candidate switches. And then here we see with a simple if question whether he or she wins or loses. Now, if I recalculate my sheet, every time I do this 1,000 times. 1,000 times I say, here's a price, here's a candidate, chooses this side, the host opens something, and then we see what happens with switching or not switching. Here, for example, right now on my sheet, it says, if you do not switch, you win 33.9% of the time. If you switch, you win 66.1% of the time in these 1,000. Now let me click recalculate sheet. Notice the number changed. 34.6% not changing, 65% probability of winning, yes, when you change. Here it's now 30.3 to 69.7. So you see, our relative frequencies are indeed close to the 1/3, 2/3 cutoff that I explained to you earlier. We can't expect that we hit it exactly, but we get very close. And I hope this convinces the last doubters among you that indeed the probability of winning after switching is twice as high as the probability of winning when you don't switch. So if you're ever in that situation, please do me a favor, switch that door. So let's go back to the slides, and I will tell you about some pop culture appearances of this problem. This concludes our look at the probabilities in the Monty Hall problem. As you can imagine, sort of a cute problem like this that comes out of a game show makes its way into popular culture. In the movie 21, there's a really cute scene where a student at MIT has to explain this problem and the solution to his professor. Please Google it and have a look at the clip. It's just 2.5 minutes. I think you will enjoy it. In 1990, there was a lot of controversy about this problem. Namely, a reader of a weekend magazine called Parade had sent in this question to a column called Ask Marilyn. This woman Marilyn is supposedly the highest IQ person on the globe, and she answers all kinds of questions that people have, whether it's in their love life, in their everyday life, or IQ related questions. Now, when she explained this solution and that you should switch the doors and that the probability then is 2/3 of winning, she received a lot of hate mail, and in particular she received more than 1,000 letters from PhDs in mathematics who were ridiculing her answer and said this is complete nonsense, it's a flip of a coin, 50-50. Now, all of them later on had to take their criticism and their laughter back when she then in great detail convinced them of the right answer. And as we just saw in the Monte Carlo simulation, I think there can be no discussion. The true number is not 50-50, it's 2/3, 1/3, and you should change. So here I give you the link of Marilyn's website, and there's a lot of entertaining discussion and a lot of these sometimes hurtful and ridiculously offensive quotes from these math PhDs. That brings us to the end of this second application after the birthday problem in the first lecture. Now we had the Monty Hall problem. This finishes our playful cutie applications. Now we move on to applications from the business world. So please come back for more applications of probability. Thank you.